Okay, student, let me start our lecture. Thank you for let me have the make a class on Thursday morning and not available. I'm going to Bangkok and also in the afternoon. PTA is supposed to taking care of you for the laboratory. And coming to the frame again, we're going to do the drawing of the shear force diagram and bending moment diagram. And as Ajahn told you, not only that one, we also require to the normal force diagram or axial force diagram when you study about the steel design for the beam column. Now, for the rigid frame, as shown over here, we have the A as the roller. So, read the problem carefully. Okay, and then we have the B as the pin. Okay, there are details here, so getting clear, even Ajahn won't provide the detail. You're supposed to be able to know this is roller, this is pin. And then for the connection C and E, they said that connection gonna be fixed connection. And following what we have studied, and I'm going to be start by first, we're going to the free body diagram of the frame, the whole frame. And as you may expect, we're going to have three unknown reaction A sub y, B sub x, and B sub y. And then we will determine the reactions that will be the same as the previous one. And following this one, we have the column AC as the shorter column. That's going to be 4 meters. Let Ajahn put this one to be 2 centimeters for 4 meters. Then 8 meters, we're gonna take it like 4 centimeters for the beam. And then that's separated into 2 portions subjected to the force over here. And then we have 7 meters. That's gonna be 3.5 centimeters for the height B for the column DE. And this is D dot, this is C, and this is F. The frame subjected to 10 kilonewton over here, 15 kilonewton over here, and then 6 kilonewton over here. Also, our frame subjected to lateral, such as for the wind load. Also, this is 0.4 kilonewton per meter. That's supposed to be the wind load. Under the given support, we will have this force to be A sub y. Since the lateral load to the left, so our reaction B sub x must be in opposite direction. And also for B sub y, expect to be upward. Okay. Now, we will start by taking the moment equation at point B as usual, because we will eliminate B sub x and B sub y out of our equation. Take moment M sub B equal to 0. A sub y will rotate clockwise to be positive, and then you got to put the moment up, and that is the reason why you got to put the leg into the free body diagram. And this is 4 meters, and this is going to be 8 meters. We have 8, and then have A sub y, rotate clockwise to be positive. Then this is counterclockwise. This one produce no moment, and this one produce counterclockwise. So minus 10, the moment arm gonna be 8. And then for this one, minus 15, and moment arm over here gonna be 4 meter. This one 6 times 0. And for the hip load, we should have the resultant of 0.4 times the length. This one gonna be 3.5 meter. This one will be 3.5 meter times 7 minus 0.4 times 7 times 3.5. And all of that gonna be 0. After you put everything in the calculator, you supposed to get a sub y to be 18.75 kilonewton, and that's going to be over here. Put it 18.75 kilonewton. Then summation of x sub x equal to 0, we will determine b sub x. Our b sub x gonna equal to the lateral. Then we have only 0.4 times 7. That's gonna be 2.8 kilonewton. Okay, and then this is a sub y. Something wrong. This is gonna be b sub x, and this is should be b sub y, and b sub x. We have this one 2.8 kilonewton, and in this direction for a sub y we have 18.75, and is upward. Okay, just check this one. The only one that you are looking for gonna be b sub y. Summation of x sub y equal to 0 upward is positive. So b sub y gonna plus 18.75 and then equal to 10, and downward 15, and downward 6. So our b sub y gonna be 31 minus 18.75. No, 725. Sorry, 725. 725. That's gonna be 12.275 kilonewton. We have this one 725, and this one 12.275, and then upward. Okay. Now we go to the second step. As before, we gonna draw the body diagram, of the frame segment. Draw the segment of the frame. Okay, of the frame, and then determine the required internal forces and moment. Internal forces and moment at the end. That's gonna be at the end. That's the ends of the frame segment. We got to separate the frame into 3 portions. Again, having the same thing as before, putting this beam at the middle. For this one, you may again put it to be 4 centimeters. Let me put this one. 1, 2, 3, and 4. And we have the force up over here to be 15 kilonewton. Okay, I should separate point C over here because it's subjected to the vertical force. And then over here, there is no 10 kilonewton, 10 kilonewton at point C. And then you have another point E. Take the point E over here. Then you have 6 kilonewton applied over here. Okay. The beam must be separate from its connection. Then we have the column. Let's take this one to be 4 meter. This is going to be 4 meter. This is 4 meter, 4 meter. And then we have another column over here. That's going to be 7 meter. That's take it to be 3.5. And this one subjected to the window of 0.4 kilonewton per meter. Okay. Then you do the projection of everything for this one. Let's take this one, and this one for the projection. This is C, D, and E. This is E. This is B. For this one is A. And this one gonna be C. Okay. Now we start our calculation. But before, don't forget about the reaction. Okay, you know reaction now. This is 18.7 to 5 kilonewton. And also for this one, we have B sub y as before, 12.275 kilonewton, and B sub x over here. That's gonna be 42.8 kilonewton. The reaction will be used to compute for the required forces and moment given over here. And you don't need to show much calculation. Let us then put this one. I think you guys are supposed to know it. Okay, and this one gonna be 18.725 kilonewton without doing the summation of x sub y equal to 0. Then the 18.725 by the third law of Newton is gonna be up to C. And then at this point C, 18.725 is larger. So the force over here in the form of shear force. There is no shear here because no horizontal force, no shear here. And also there is no moment here because over here there is only axial force. Okay, no moment, no shear, only axial force. Right? I like the previous one. And this one, you should have this one in balance. This one should be 8.725 kilonewton. You may not need to do the calculation. I believe you guys learn a lot. You should know about it. Okay. Now, the 8.725 downward will apply over here to be 8.725 kilonewton upward. Okay. Now, we may go to the column over here, or you may select this one. It's up to you. For this one, again, 12.275, you should have the force 12.275 kilonewton, and then it's gonna act upward. 2.8 over here. And then you also have this one, the shear force over here, the shear force over here. If you do the calculation, this one going to be 0.4 times 7 is also 2.7 kilonewton. So the shear over here gonna be 0. The shear over here should be 2.8, and this one gonna be 2.8. Then due to this 2.8 and this one, we supposed to have the moment over here. Let Ajahn call this one to be M, and this is going to be E. Do the summation of the moment about point E equal to 0, and put this direction of the moment to be positive. So we have M sub E in this direction. The moment arm, this is going to be 7 meters. This is going to be in the opposite direction, minus 2.8 times 7. And then we have the moment to this 2.8, but the moment arm over here going to be 3.5 plus rotate in the same direction in sub E, 2.8 times 3.5, and everything supposed to be 0. Okay, and then you should have M sub E. Okay, the M sub E gonna be 2.8 times 3.5. That's gonna be 9.8 kilonewton. 9.8 kilonewton meter. And again, follow the third law of Newton. This is going to be the moment 9.8. And this one gonna be the moment 9.8 kilonewton meter. And also this one. Okay. Now 12.275 downward. We will have this one to counteract it. And then following this downward, we will have this one upward, and it's 12.275 kilonewton. Now, when everything ready, you may check, okay, for this one, summation of x sub y, summation of x sub y, if you put it equal to upward 8.725 minus 15, and then this is plus upward 12.275 total 0 is going to be correct. Okay, the force upward, this one downward, this one upward, this one combination going to be 0. Okay, upward, downward, upward. Okay. And then this is 8.725 is over here. This is 12.275 downward, upward, downward, upward. Okay. Take the third law of Newton. It's not 0. Oh yes. Yes. I forgot one thing. Thank you very much. I just forgot this one. This one 12.5 up, minus 6. This one supposed to minus 6. And then this is going to be 6.275 kilonewton. Thank you very much. Okay, this is going to be 6.275. I forgot. I really beware about the force and the charge, but this one I forgot. Okay, thank you. And then you check the moment. Okay, summation of the moment at, for example, at C equal to, if you put this one to be positive 9 point 8 in this direction, and then plus 6.275 times the length of 8, and then in opposite direction minus 15 times 4. This check for me is supposed to be 0. Okay, it's supposed to be 0. Thank you very much. Okay, that's one. Now we are ready to the third step. Okay, the third step we will draw the shear force diagram, bending moment diagram, and also axial force diagram or normal force diagram. And again, start by rotating it, and we will have start from the bottom to the top for this 4-meter column. Now, for this one, we have shear force at x meter, start 0 over here and 4 over here. Do we have shear force for this one? We don't have it. We have only this 18.725. So our shear force is 0. W is 0. dV by dx is 0. At the end, this column subject to no shear force. Okay, don't panic. It's no shear force. It's no shear force. Then come from the moment diagram and follow what we have over here. We put this one M in kilonewton meter. This is roller and no external moment. So the moment over here gonna start from 0, and then the shear is 0. So we have df by dx equal to 0. Then there is no moment on this column. Okay, and the last one for the axial force, we have 18.725 in compression. So the normal force over here gonna be in negative. Okay, in negative. So if you put 20.5 millimeter, this is gonna be minus 18.725, and it's gonna be constant minus 18.725 kilonewton. We have all the required diagram for our column, and then move it to the beam. Okay, move it to the beam. We supposed to hit more, and for the beam here, we start from the shear force diagram as before. We have the beam with 8 meter. This is x meter. Put this one 0, 4, 8, and then this is going to be V in kilonewton. We have this one upward force 8.725. So you may put this one here force. This one 8 plus 8.725. W here is 0. dV by dx is 0. Then this is constant and plus 8.725. Then we have 15. That's going to be about 15 millimeter minus 15, and then plus 8.725. as you can say, this is going to be negative 6.275, and W is 0. dV by dx equal to 0. This is constant. And over here, upward force, close it. That's going to be your shear force diagram of the beam. Now, come to the bending moment diagram. We have x meter again and 0, 4, 8, and this is going to be our m kilonewton meter axis. So starting from C, no moment. So we have 0 moment over here, and then shear positive. So we have slope upward. We have dm by dx equal to plus 8.725. And what we have to calculate is the moment at 4 meter or at D. M sub D over here, M sub D over here, minus over here, 0 is going to be equal to this area for 8.725. So our M sub D again got 34.9 kilonewton meter. Okay, so you may put it with a proper scale. 10, 20, 30, and 34.9, about 35 is going to be over here. You may take this one and point it over here. Okay, we need to write it again and then draw the line. We have the slope 8.725. Now, what is going to be the moment over here? It's going to be m sub e, this is e, minus over here 34.9, and then it's going to be equal to this area minus 6.275 times 4. Okay, and then you will get m sub e. You should get m sub e to be 9.8 kilonewton meter, and it is positive. Okay, so this is 10. This is supposed to be 9, and then the slope dm by dx gonna be minus 6.275. We have the line like this one. You may highlight it if you prefer. Then you have this counterclockwise. So the moment here 9.8. Okay, 9.8 gonna take downward and put it back over here. Okay, and then for the last one, do we have axial force? We don't have axial force on this one. X meter. Put this is going to be n in kilonewton. No axial force. 0 and 0. No axial force. Okay. Then and then flip it now for the column BE. Okay, column BE. We start with our shear. Okay, and then this is downward. We suppose start with the shear with the negative. So this is going to be our x meter, and this is 0. This is 7, and our axis we kilonewton. Newton. 2.8 downward. Okay, 2.8 downward. So we have this one for negative minus 2.8. Then, guys, this one is what? Upward. Okay, so dv by dx gonna be minus of the minus 0.4. Slope over here gonna be positive 0.4. Okay, this is upward. Okay, so it's negative. Okay, and then here is 0. You have this one to be 0. Then our shear force diagram, you have a shape like this one. Okay, negative. And then for the moment, we draw again. This is going to be x meter, and this is going to be the moment in kilonewton meter. Start from 0 to 7. Do we have the moment for this one? No, no external moment. So our moment start from 0. Then we have the here negative. So dm by dx gonna be minus 2.8. It's gonna be something downward like this one. And then what's going to be the moment over here? You have 9.8. Okay, believe me, this is going to be minus 9.8. Okay, but thinking about, we don't know about it. So m sub e over here minus 0. And then it's going to be equal to the area over here minus 1/2 times the length of 7, and this is 2.8. Okay, you will have m sub e equal to minus 9.8 kilonewton meter as expect. Okay, this is going to be minus 9.8. And then slope over here will be 0. Here over here is 0. So dn by dx over here gonna be 0. Our graph will be something like this one. Okay. Slope change for minus 2.8 to be 0 here. And this is gonna be negative bending moment. Now, the last one, axial force compressive, is going to be negative. Okay, this one and this one, and in kilonewton x meter, negative of what? 12.275. Okay, this is 18.725. And then that's going to be this one minus 12.275, and then constant minus 12.275. Then you get this one to be axial forces diagram or normal forces diagram. Now you have everything. Okay, you have all the diagram. You got to combine them together by drawing our frame. Okay, and then follow as before. We may have normal force diagram for centimeter, and this is 2 centimeter, and this is 3.5. It's gonna be shear force diagram, and then the same over Here we may draw again for bending moment diagram. This is bending moment diagram. And then the last one, you may draw it over here and 2 meter here and 3.5. Okay. Then copy what we have. Okay. This is the shear force. Notice just put this one 0, this one 0, dv by dx equal to 0. Then copy this one 8.725. Okay, you can put this one up plus 8.725, and then it's going to be constant for 2 centimeter. This is going to be plus 8.725, and then it's head downward to minus 6.275. Just head it, and then indicate dv by dx equal to 0, and over here also dv by dx equal to 0. For the shear force over here, minus 2.8, that's going to be very small compared to 6 and 8, minus 2.8, and then take this one down to be 0 over here, and we have dv by dx equal to plus 0.4. Okay, please combine them like this one. For the moment, again, over here is 0, over here is 0. We have dm by dx for AB equal to 0. Then take this one. Okay, this is going to be about 1.5. And this one up. And then we have to copy this one. 30. This one 34.9, and dm by dx is gonna be plus 8.725. Then copying it over here, this is going to be plus 9.8, and take this one and make the slope dm by dx equal to minus 6.275. Then for this one, okay, we have this is going to be minus 9.8, and this is 0. Our slope here, over here is 0. dm by dx equal to 0. Over here, minus 2.8. This is dm by dx equal to minus 2.8. Then you have the curve of this one. Okay, that's the curve. Okay, that's going to be bending moment diagram. This is positive. Okay, and this is going to be negative. Okay, then the last one, minus 18.825. If we put this one, and then this is going to be our normal force diagram, axial force diagram, minus 18.725 minus 18.725. No, axial force to the beam 0, 0. This one minus 12.275, and this one, and minus 12.275 minus 12.275. We have our normal force diagram, bending moment diagram. Okay. Then there are two more important things for the bending moment diagram as we draw the elastic curve. Okay. Now, Follow what we have over here. We may try to draw the elastic curve basis on what we have here. Okay, and for the frame subjected to the bending, the frame will bend basis upon the support condition. Let Ajahn put this one to be the roller. Sorry, this one to be the it. This one to be the roller. Okay. For this point B, since this is roller, V sub dx equal to V sub by linear displacement gonna be 0. Okay, and then over here we should have theta sub b won't be 0 since our frame subjected to lateral load also subjected to lateral load like this one also. One more thing Ajahn should mention is going to be the roller at point A. Roller can move in this direction. So V sub AX won't be 0. However, it has reaction A sub Y. V sub AY gonna be 0. So the movement supposed to be only in the horizontal direction. How about theta sub A? Theta sub A won't be 0. Now, due to the application of the force lateral load, the frame subjected to this one. So if you put this one, you bend it. This one should be moved like this one. Okay, follow this kind of bending. So it's gonna bend something like this one. Okay, rotation then we will have this kind of elastic curve for our plane. It's gonna be curve. Okay, it's gonna be curve. Then over here, rigid joint. This one must be kept 90 degrees as before. And then subjected to the moment like this one. If this one moves in this direction, let me put this one. This is put in this direction. This is 6 kilonewton. This is 15 kilonewton. This is 10 kilonewton. And then it have lateral movement for 7 millimeter. So this one should move over here. Should move the same as this one. Typically, we call this one delta. Delta is going to be lateral displacement. Then, due to this bending, seem the same as we have for simple beam. Our beam will bend like this one. Since this is normal, so you got to keep this one in normal direction. So this one must be kept in normal. Then over here, we will have the roller. Okay, the roller. This is going to be A and then B and then C, D, E. Okay, and this is going to be delta or V sub AX as Ajahn mentioned over here won't be 0. And also over here, this is going to be theta sub A. Again, over here, if you measure it, this is going to be theta sub b, okay, and this is going to be delta E, and this is going to be delta C, and then the slope you may measure over here due to rigid connection. This is going to be theta C, and follow the same as that one over here. You will have the slope. You will have the slope. This is going to be theta E. And all of this, we call it elastic curve. Okay, this is called elastic curve. Drawn from the moment diagram. Okay. Then there is another thing. If this is the steel, is okay. But if our structure is not steel, it is the reinforced concrete, you may use this moment diagram to draw the reinforcement for this one. And then you must put this one. If this one is the reinforced concrete, and then putting this one to be lower, and this one to be hit. Okay. For the reinforcement, most of the time we will have the minimum requirement of the reinforcement, and then we just follow, such as for the column, we must have 1% of the reinforcement. Then following what we have here, okay, we only use this one to put extra reinforcement. This one has no moment, no extra reinforcement for the column. This one positive, okay, and then signal 2 is positive. So you should add extra reinforcement for this moment, okay, to taking care of the bending on the bottom of this one. This one also is going to bend like this one. This surface is going to be in tension. So for this one, you may put the steel, extra steel, only for this two times red. Okay, the red. No need for this one. This is for reinforcement. Okay, for RC frame, but this is just a starting point. In the midterm examination, Ajahn will not ask you for this thing, but later, Ajahn will. Okay, we will have this kind of development in our civil engineering skill for reinforced concrete. Then, in chapter 8, I think the last chapter, before the last chapter, we will determine all of this deflection. We will study about how to determine the deflection, then we will draw the elastic curve. So that is all for our chapter 4, and we are ready to have midterm examination. Okay, class, let me move you to the next chapter, and we are going to analyze the statically determinate cable and arch. If you go to the Google and try to search for this kind of structure, you may find the suspension bridge over here called Golden Gate Bridge in California is one of very renowned masterpiece of the suspension bridge. This one subjected to both hurricane and also the earthquake, and it still stay there since it was built. Some people say one of the end of the bridge had been moved for like 2 meters from the original due to the earthquake. And then if you go to the Europe, there are very beautiful bridge that's built by using the arch. Unlucky in Thailand, we don't have this kind of structure, but I believe in the future, this kind of structure may be built in our Asian country. And then the learning objective, I prefer you to understand and be able to analyze the statically determinate cable subjected to concentrated load and uniformly distributed load. For the concentrated load, we will base on our knowledge from engineering statistics that we will use what's so called the equilibrium of particle. So this one is not much tough. The other one, the cable, such as in this golden gauge width, is subjected to uniformly distributed load because this kind of bridge has a number of anchors. So the force on the bridge over here will transfer to the anchor and then transfer to the cable. Since the distance between anchor is small, so we can assume that cable subjected to this kind of distributed load. This is one of new thing. Now, we also have the reverse. Cable, as we know, is in tension. The cable is the same as the wire over here. It cannot subjected to compression. But the arch is the reverse of the cable. So most of the arch is going to be in compression. And since the old day, there are many structures built by the arch because at the time we use rock to build large structure such as churches. Okay, so arch from the compression member, then the rock is going to be very good material for the arch in the past. But nowadays, we use a lot of steel to build arch bridge. And for me, I think this kind of structure is very elegant. Now, there are some homework for you guys to work on, both for the cable and for the arch. An arch can be the hinges, touch arch, not only to be the spandrel arch like this one. The touch can be from the arch also. For the cable, most of the time is used to support the bridge, okay, and subjected to uniform load. Now, coming to the cable, as Ajahn mentioned, there are models of the suspension bridge based on many renowned suspension bridge. And excepting from what I'm saying, the golden gauge bridge of California, we still have Akechi Kyoyo bridge in Japan that can span total of 3.6911. That's total length of 3.6911 meters with the longest span of nearly 2 meters. This huge structure can only be made by using the suspension bridge, and the suspension bridge usually is the one that has the longest Spanish. There is another one in Turkey. I will mention it later. By putting this one, all of the cable of the bridge gonna be used to carry the weight from the bridge deck, passing through the hanger, and then the cable will develop the tension in itself without shear force and bending moment. And the cable in our study, we assume it to be perfectly flexible and is inextensible, no elongation. Since elongation is very small compared to the total length of the cable. Okay, you may go to the link under it, okay, to read more for those kind of stuff. And this is going to be one topic. To decide whether the cable is subjected to concentrated load or subjected to uniform load is based on the distance between the hanger. Okay, this one is for the pipeline. We have the pipeline to transfer the crude oil from one to the other side. And if the distance between the hanger is small, we may assume this one to be distributed force. But if the distance is large, we will assume it to be concentrated load. For example, if you go to Singapore, okay, you may go to this website also. This Singapore cable car, there are the weight of the cable car putting on the cable. Since the spacing of this one is large, then this kind of cable got to assume subjected to the concentrated load. And the model of this one is going to be shown over here. Okay. Then there are many bridges in the US. This is going to be another one called George Washington Bridge. It's going to be a suspension bridge, the same as the Golden Gate Bridge. The hanger, the distance is very close. So the cable on this bridge is subjected to uniform load. Okay, and due to this kind of uniform load, the shape of the cable gonna be in parabolic shape, and then you get the cable equation. Okay, and for this one, another assumption must be assumed. The weight of the cable is small compared to the weight, the loading the cable carry. Now, the example of another cable subjected to concentrated load. Again, this one spacing is quite large, so you may calculate, analyze this cable of the bridge to be subjected to concentrated load. And then there is another thing for the engineer who working to build the electrical transmission line and power. Okay, this kind of cable is not subjected to concentrated load and also subjected to uniform load. This kind of cable subjected to its own weight. And the shape of this cable is in the form of catenary, different from parabolic shape. And you can read this more on the engine static textbook. Okay, Professor Hitler textbook or Professor Bian textbook. This is gonna be your additional, okay, additional self-study if you like to study it. For the textbook of Professor Hitler also have it. But since our work concentrated on the load of the bridge, so we will study that. And there is another thing that's different from suspension bridge. If you go to the Bangkok, there are many cable stay bridge building in Bangkok. This one is King Lama 8 bridge is one, I think is one of the most beautiful bridge in Thailand. And then they are different from what Ajahn mentioned about Golden Gate Bridge. The way to study it, you're supposed to study bridge engineering, another subject for you. And now let me move to the first one. Cable subjected to concentrated load. We start with indicating the weight of the cable because it's so small compared to the concentrated load. And most of the cable built by isotopic homogeneous material. It may be steel, it may be aluminum, and have linear elastic behavior, small deformation, and that's one going to be negligible deformation also. Then we can analyze it by using the method of joint and the method of section that we use in the past. Then for the method of joint, each part of this one, you should have two equations of equilibrium. Then for each joint, you can solve for two unknowns. But if you consider this one for the whole cable, now you may think this is going to be T, then this is A sub X and A sub Y. And since this is the cable, if you cut it, this may be T sub B D. No need to separate this one to be B sub Y and B sub X. You don't. Okay. If you draw the free body diagram as this one, you may take the moment at point A, and then you may determine T sub BD, and later you can determine A sub X and A sub Y, and also later you may distribute this one to be this B sub Y, and then this is B sub X. You can determine the reaction due to the applied force by consider the free body diagram of the whole cable. Now, following the example, okay, the cable in our study is going to be statically determinate cable. That means the free body diagram should be draw and use equation of equilibrium to solve for the unknown. For this one, they ask us to determine T sub AB, the force in this cable, T sub BC, the force in this cable, and T sub CD. And then also for the distance H here. And Ajahn should say that basis upon this one, the cable have four unknown reactions. That's going to be A sub X, A sub Y, and then D sub Y, and then D sub X, and then three force in the cable, and then one more for the H over here. Total going to be 8. We can solve it, okay, by consider joint A, consider joint B, consider joint C, and consider joint D. We have 8 equilibrium equation. This is statically determinate cable. As Ajahn mentioned, to determine the reaction, many times we consider the whole free body diagram of the cable system. By doing that over here, we may consider A sub X, A sub Y, but at this point, as Ajahn mentioned, since cable subjected to the tension, you may cut it before the support. Then you get the T sub CD over here. Now, take the moment at point A, you will determine T sub CD. But before that, again, you got to take the component. Since this cable have horizontal 2, have vertical 3, the ratio over here gonna be 2, 3, and square root 13. So the component in the x gonna be T sub CD times 2 over square root 13, and the vertical gonna be 3 over square root 13 times T sub CD. Take the moment about A by putting the rotation over here to be positive. So this one will time the moment arm of this whole distance 2. This is gonna be 6 meter. The force here times 6 meter counter clockwise positive. Okay, and then there is another component cockpit that's gonna be projected the line of the force in this direction, and the moment arm of this one gonna be 1 meter. However, the rotation is in this direction, so negative. The force and then times the moment arm of 1 meter, you get this one. Then 50 kilonewton have to time moment arm of 4 and rotate in this direction negative. And this one also 10 times this 2 meter rotate in this direction. Both of them gonna be negative 10 times 2 and then negative 5 times 4. You saw from T sub CD, you get T sub CD to be 9.414 kilonewton. And then you may draw the free body diagram of the joints. And I should say there is the joint over here. Okay, if you draw the joint D dot, then you may find the reaction 9.014 gonna be third law of Newton in opposite direction, and then you may determine d sub x and d sub y. Actually, this is going to be the d sub x, and this one gonna be the d sub y, the same. Okay, by the third law of Newton, and then you may get the reaction d sub x. And Ajahn should note it on the d sub x. Okay, we will have the note on this one later. Now, we have d sub x equal to 5, d sub y equal to 7.5. Then, summation of x sub x equal to 0. You have a sub x to be 5 kilonewton. Then, you may also have the summation of x sub y to be 0. This one you put upward to be positive. So this one plus 7.5 gonna be a sub y plus 7.5 equal to 10, and then plus 5 you get a sub y to be 7.5 kilonewton. Okay, that's gonna be the reaction. Now, you may use the method of joint to cut over here and draw the free body diagram over here. Since this point, you have only 2 unknown. But for this one, you don't know the force here yet. You don't know the force here yet, and you also don't know the slope here. You don't know the slope here. So this is not a good choice. You will start with choice C. Okay. Since this is the ratio as before, 2, 3, we have this one, square root 13. For 2 unknown, you may do the summation of x sub x equal to 0. Then this one is going to be positive, and the component of this one going to be negative. Now, there is another question. You have the third question. Summation of x sub y. You have this one to be upward positive, and this one to be downward negative. You have two equations, and you're going to solve it for theta sub bc, and also to solve it for t sub bc. How to solve it? This one you got to write it again. Okay, for this one you will get t sub bc cosine theta sub bc equal to this one 9.014. That's going to be the force in the x direction. You will get this one to be 5. Another one going to be 7.5. Okay, that's one going to be equal to 5. And this one, we write it again, t sub bc, and then sine theta sub bc. This one going to be equal to 7.5 from the previous slide. Now, we have this one and this 2. Take the 2, divide by the 1. You will have sine theta sub bc over cosine theta sub bc equal to 7.5 times 5. That's going to be tan theta sub bc. So you will have theta sub bc equal to arc tan of 7.5 divided by 5. Okay, you should get this one. Did you get it? Check. You may check this one. Where is my report? Okay, over here. You may check this one. How come I won't have scientific calculator? Take this one. Did you get this one? No? You don't get this one? Something wrong. You may take this one. What will get this one? 9.014 times 2 divided by root 13. That's going to be 5. Minus 5. This is going to be 2.5. This is supposed to be 5, right? This one will be what?
7.5 and we forgot.
How come it's 7.5? Because it's supposed to be the same as we have it over here. The x is supposed to be 5. The supply is supposed to be 7.5.
Yeah, the first one is correct. The second one is not 7.5, it's 2.5 because we have.
Oh, this one.
Yeah, that's
Let me take this one. This is not correct.
This is correct, but we have minus 5 in the equation.
Okay. You mean this is going to be what?
That's 7.5.
7.5. This one will be
in the upward equation. Minus 5.
Let's see. This one is this one gonna be 2.5. Okay, thank you very much. This is going to be 2.5. I'm sorry, I didn't see this one. Since we have the load over here also, right? Then this is going to be 2.5 divided by 5. This is going to be this one. And then you get this result, right? Okay, get this result. Then you take this one back and replace this over here. You will have T sub BC equal to 5. divided by cosine 26.565 degree. Then you get T sub BC. Okay. Now, the force T sub BC is known. That means the force over here is known. The angle over here is known. That means the angle over here is known. You are ready to cut point B. Okay. Now, let me erase everything. Now, for this one, we have the force here. We have the angle here. We're going to solve the same thing. Okay. Project all the forces in horizontal direction. This is 5.59 and then cosine 26.565 and this is positive. For this one, it's going to be K sub AB cosine theta AB is going to be negative. And for the vertical, you solve the same way discussed before, we get T sub AB. Now, the T sub AB is 9.014, larger than T sub BC. Okay, and then we solve more. Since this is going to be the angle, okay, so H over 2 gonna be tan of 56.31. You can solve for H to be 3 meters. Okay, and then for the length, you may determine the length of this one plus the length of this one, and then plus the length of this one. You may get the total length of the cable also. And then how do you get this one? You get this one. Okay, it's not that hard because the angle over here is 46.31. This is L. Okay, we have L and then cosine 56.31 is gonna be 2, right? So the length L sub AB cosine is 2 meters. So you get this one. And then since the angle here and the angle here 56.31. So you times it by 2. For L sub BC, you got to take this one. L sub BC cosine 26.565 degree equal to 2. You get this one. Okay. L cosine. Then there are some notes that's important. If you recall from it, you will have A sub x and A sub y to be 5 kilonewton, 5 kilonewton. And then if you take the force over here, the force over here, the force over here, also the force over here, I take the force in this portion, that's going to be 5.59. Okay, this one have the tension 5.59. If you try to project it, this is going to be 5.59 cosine 26.565, and then this is going to be 5 kilonewton. The component of all horizontal force, not only the reaction, also of the cable tension, the component of them always equal. Okay, and this one will be extended to the cable subjected to uniformly. And then second thing, the maximum tension. The maximum tension over here occur on both cable AB and cable CD. since the angle over here, they are the same. Okay, maximum tension in the cable system is occur when the cable has the largest slope with respect to the horizontal line or the largest theta. This one also will be used on the next portion of our lecture. Okay, this is 29.014. And how to design the cable? You got to go to mechanics of material. We have sigma equal to T over A. Sigma gonna be sigma allowed. T gonna be T max. A gonna be A required. Then our A required gonna be T max over sigma allowed. Now you can determine the section of cross section of the cable easily. Okay. Then we have many examples in our PowerPoint, and this one pretty the same. You are determine T sub AB, T sub BC, T sub CD, and then H. That's one going to be the same as before. Okay, and then do the same thing, do the calculation, and then you can go to all of this by yourself. Solving for the slope and the tension in the cable, and then following all of the example over here. I will assign you to read it by yourself, or you can go to my video clips. Okay, for our study, you may study it by yourself. Okay, that's supposed to come to the end again. The horizontal force of the reaction and of the tension gonna be equal, and this one follow the maximum tension gonna occur on this one. Since this one has the maximum slope with the horizontal, okay, gonna occur on the segment AB since it has the higher slope. And then how to determine the set? Okay, you can look it to the same as before. And that's the end of the cable subjected to the point load.
Hello, my student. This clip, I'm going to show you how to solve the cable subjected to the concentrated force. The cable we have here have the joint A, B, C, D, and E, and it has the pin support at A and pin support at B. Let me keep the color of the cable like this. AB is yellow, BC is the green, CD is the light blue, and also the last one, DE, is going to be orange. The cable is subjected to 5 kN at B, and P1 at C, and P2 at D. So they are asking us to determine the magnitude of the force P1 and P2. And then they also ask us to determine the maximum tensile forces in the cable. And later they ask us to determine or decide to find the diameter of the cable. Okay, when we have the cable like this, and you know that the A and E is the pin, you will see that the point E gonna have two unknown like this. That's total of 4. And another problem is we don't know the P1 and P2. When we don't know the P1 and P2, we cannot determine the reaction. Okay, and that means we cannot use the free body diagram of the cable system to find the reaction. Okay, since we don't know, since we do not know the P1 and P2. Okay, so what we have is thus we need to draw the free body diagram of the joints and use the equation of equilibrium to find what? To find the P1 and P2. Okay, before we can determine the reactions. Okay, then if we have that, this is our first consideration. So next we got to do that. We draw free body diagram of joints, what? Joints B, C, and D, and use the equation of equilibrium, okay, to find unknown. Okay, that is repeat this unknown P1 and P2. Okay, and if that the case, we supposed to project what we have here downward and draw each joist properly. Okay, we start with joist B here, and for the parallel you may have this at the joint C, and also if you project it horizontally you will get this the point D. So this is a B, C, and D. And you also need to put the X and Y axis to have the reference for each joint. Okay, and we have this. Oh, sorry, we have this. This is X, and this is Y. We have three choices. So which one gonna be the first to consider? Usually, since we know the force here, we start by this joint. We start at joint B because we know this is 5 kilonewton. And due to the 5 kilonewton, they are going to have this force in the cable AB. So we have this force. Let's call it T sub AB. And we also going to have this force. This is going to be in the BC. And due to the third law of Newton, so you're going to have this also. So this is going to be T sub BC. And then for the CD, you also going to have the unknown due to the applied force P1. So this is going to have the unknown force of T sub CD. And then due to the P2, you're going to have the tension in this cable. Let's call it T sub DE. Okay, we have all of the free body diagram, and then you got to determine the angle that the cable act with the horizontal axis. The first one here is equal to this one. Okay, for the cable AB, and you can see if this, let's say, if this is going to be theta, you have this for 1.5 and you have this for 2, so the theta is going to be 1.5 and then divided by 2. and then you get this angle for 36.87. 36.87 degree. Okay, this is going to be 36.87 degree. And you also have the angle here, which is going to be equal to this one. Let's call this is the phi. This is phi. This phi is going to be inverse tan of what? Of this. Since the angle is here, it's going to be this. This is going to be 1, and this is going to be 4. It's arcsine of 1 over 4, and then you get this for 14.04 degree. So the angle here is 14.04 degree, and it's going to be the same as this angle. Okay, this in horizontal is okay. And the last one, we have the angle here, and let's call this is alpha. Alpha going to be this length and this length. Tan alpha going to be this. What is going to be this? This is going to equal to this distance. That is going to be 2.5. So alpha is inverse of tan 2.5 divided by 4, and then you get this for 32.0 degree. So over here you got the angle of 32 degree. And now you can see the free body diagram here gonna have 3 unknown. This one also has 3 unknown, and it's better for us to start by consider the choice B. Okay, let us consider free body diagram of choice B. We should start it first because we have 2 unknowns, we have 2 equations, so the unknown force can be determined. So summation of x sub x equal to 0, and then if we put this as positive, what we get is we're going to have t sub bc, and then if we project it horizontally, it's going to be positive. So the first one, we're going to have t sub bc. The t sub bc going to be cosine of 14.04, and it's going to the right. This one, when you project, okay, you may see this one got to be in the left, so this one going to be minus, and then this one is t sub ab, and it's going to cosine 36.84. Okay, and that's all for the horizontal. You get this equal to 0. You cannot solve yet, okay, but you can determine the relationship between t sub b and t sub a. So now your t sub bc, okay, if you move this, is going to be equal to t sub ab, and then you have this, you move this one, and then this is going to be cosine 0.84 degree divided by cosine of 14.04 degree. And if you stop the clip, try to put this into your calculator, you will get this coefficient, and you will have it for 0.8246. This is 0.8246. Okay, that is the first one. We don't have the results of this yet, and then we go further by summation of f sub y equal to 0. Now if you project this, it's going to be up, okay, and if you project this, this is going to be down. Let us put the upward is positive. Put the upward is positive. So you have t sub ab, and then when it up like this, it's going to be sine 36.87 degree, and then 5 is down, minus 5. And this one also, when you project this, the T sub BC gonna be downward, minus T sub BC, downward, T sub BC sine 14.04 degree, and put this to be 0. That is the equilibrium of the horizontal force. And if you do this, you may get what? T sub AB and sine 36.87 and minus, you got T sub BC here, right? That is going to be 0.8246 T sub AB. This is going to be sub BC, and then it's gonna sine 14.04 degree, and then it's gonna be equal to 5. And then you put this into your calculator, you will get the T sub AB of what? T sub AB. Your T sub AB is going to be equal to 5 divided by, take this one out, sine 36.87 degree minus 0.8246 and sine 14.04 degree. Okay, and then you get this T sub AB of 12.5. Okay, this is going to be the 12.5 kilonewton, the tension. So the first result of T sub AB is here. And now, you know T sub BC, right? You just put this one back into this. You will also get T sub BC equal to what? 0.8246 and time 12.5. So you get this T sub BC of 10.31 kilonewton, and it's also in tension. So what we have here, 10.31 is the force in the cable BC, and this is going to be the force in the cable AB. So you get this T sub AB, and you now get this one for the T sub BC. When you know T sub BC and you consider the free body diagram of joint C, now you only have the P1 and T sub CD as the unknown. So by this, we go the next step. Consider free body diagram of joint C. Next, we consider the free body diagram of joint C, and you may take this one. So since this one is the force, the no force of 10.31, let's say this is 10.31 kilonewton. So it is project in the x direction. It's gonna have this direction. So just summation of x sub x equal to 0. And then you get this T sub CD, this is plus. You may get T sub CD to the right, and this one is to the left, equal to 10.31. And when you project to this, it's going to be cosine 14.04 degree. And now you get the answer easily. That is going to be equal to 10.0 kilonewton, and it's in tension. Okay, and T sub CD is 10. That means this is 10 kilonewton, and this force is the light blue here. We know this force T sub CD. Okay, and if you summation of f sub y equal to 0, this time you're going to take for the P1, so it's downward. That's downward is positive. The P1 downward, and this one, if it's project, it's going to be upward. So the P1 is going to be equal to, this is 10.31 and then it's going to be project to this. It's going to be psi. Okay, and then you get the result. Just put into your calculator. You got P1 of 2.5 kilonewton. Okay, you get P1, and the P1 is 2.5 kilonewton. 50, if you like, 50 kilonewton, and it's downward. Okay. Now you get this P1 of 2.5 kilonewton. Now you can move to consider joint C. So consider free body diagram of joint D. Okay. What we have is there are two unknown, is the T sub DE and P2. If you project this force into the vertical direction, you get two unknown. If you project this one in the x direction, it's gonna be T sub DE cosine 32 degree, and you're gonna have what? Only one known. So we do the summation of x sub x equal to 0. And since this one to the right is positive, okay, you may have this T sub CD, DE, and project into this cosine 32 degree. And then this is going to put in the opposite direction. So it's going to be 10. And now you may have T sub DE, equal to 10 divided by cosine 32, and you get the T sub DE of 11.79 kilonewton. Okay, this is going to be the orange T sub DE, and now you get this. And finally, if you do the summation of f sub y equal to 0, and P2 is downward is positive, so the P2 is here. And the P2 is what? P2 is downward, and this one is upward, so it's going to be equal to 11.79, and this is going to be sine 32 degree. And if you put everything in your calculator, this is going to be 6.25 kilonewton. So now we have this one of 6.25 kilonewton. Okay, by doing this, we have P2 of 6.25 kilonewton. So this is going to be 6.25 and downward kilonewton. Next, we're going to determine the maximum force. So let's see. Find the maximum force in the cable. Okay, as you may see from our calculation results, what we have here is the force here is 12.5, 10.31, 10, 11.72. So the T max is going to be T sub AB, right? Consider the forces obtained from 2. We have T max equal to T sub AB equal to 12.5 kilonewton. That's it's going to be 12.5 kilonewton, and it's in the cable AB. So you just answer this, going to be 12.5. Okay, and note, you should note. That's okay. T max occur at A, B, having the angle with respect to having the highest angle with respect to the horizontal line. Okay, you may see that is going to be 38.84. This is 14.04. This is 0. This is 32. So it's occur in the cable having the highest angle with respect to the horizontal line. And also in the opposite Tmin occur at the cable CD, okay, having the lowest angle with respect to the horizontal line. Okay, that is going to be okay. And next, we can determine the reaction, and if we take this one a little bit down. Okay, up until now, we can calculate the forces in cable AB, BC, CD, and DE. Now we can calculate the reaction, for example, at point A. Okay, let us consider. Okay, let us consider the reaction, and if you may see the free body diagram of the joist A, if you take the joist A here, you may have this is the A, and you also has the force. Since this force is pointing up, so at this joint you also have this for 12.5 kilonewton, and also since the angle here is 36.87, okay, so the angle here is also 36.87 degree, and you may have this of A sub x and A sub y. So this is going to be the A sub x, and this is going to be the A sub y. And by considering this, you may determine the summation of x sub x equal to 0. That means you're going to project this, okay, and then you put this one plus, so your A sub y right here, and this one gonna cosine, so it's gonna equal to 12.5 and cosine of 36.87 degree. So you can get the A sub y easily, and A sub x, you can get A sub x equal to 10 kilonewton. That is A sub x. For the A sub y, just do the summation f sub y equal to 0. So this time up is plus, and then now you get A sub y is up, A sub y up. The projection of this is going to be downward, so it's gonna equal to 12.5, and then it's going to be sine 36.87 degree. So put it into your calculator, or you may stop the clip. What do you get? It's going to be 7.5. Okay, that is the reaction. The A sub x is 10, the A sub y is 7.5. So if you put it into this is going to be 10 kilonewton, and the A sub y is going to be 7.5 kilonewton. Okay, if you consider this, and let me take this in your consideration, you may see that what we have is the reaction here. So we can determine the reaction here. Let me put it over here. Okay. Phi reaction at E. And then you may have summation of x sub x equal to 0. This E sub x. This one is positive. So E sub x is going to be what? It's going to be equal to 10 kilonewton. Okay, this is going to be 10 kilonewton. E sub x equal to E sub y. Oh, and also equal to CD. And summation of f sub y equal to 0, pointing up positive. So E sub y plus 7.5. And then it's going to be minus 5 minus 2.5 P1 and minus 6.25 over here is 6.25. And then it's going to be 0. If you do this, do E sub y cut, going to be equal to 6.25 kilonewton. So this one is 6.25 kilonewton. And you're going to have another observation. You may see the force E sub x, the force A sub x is equal to the force of T sub CD. And if you project all the horizontal force, you may see that the horizontal force component in each cable and reaction are constant. They are all constant, and this is important. It help us to check whether our calculation is correct or not. Okay. The last one, we determine the diameter, and then we come to our cable. Our cable have the maximum tensile force here on the cable AB. So the last one, that's for design the cable. Okay, and Tmax equal to T sub AB equal to 12.5 kilonewton. And what we have from the mechanics of material is when the cable subjected to the forces, the cable will have the stress in its material, and the stress is equal to the force divided by the area. And since the Tmax, we will produce sigma max, and then in the design we going to find the A, and always we going to set this sigma max as high as of sigma allowable. And if you go here, you may have this, the allowable tensile stress is 100 megapascal. Even though they said they use the factor of safety of 2.0, you don't need to consider this because this is already allowable. So by doing this, you may get the equation of the A required. You put the A required up, okay, and put this one down. It's going to be equal to Tmax divided by sigma allow. Okay, and then you're going to have this one as equal to what? 12,500 Newton, and divided by 100 Newton per millimeter square. The unit of Newton per square millimeter is the megapascal, the same one. So you got this of 125 square millimeter. And now you have what? You have pi d square over 4 equal to 125. So you can solve it for d equal to how many millimeter? You can get it for 12.62. Okay, that is going to be our answer for this problem. It's going to be 12.62. 12.62 is about 13. That is kind of a size of the cable. And this is going to be 13. Well, this is about the size of the cable used here for 12.62. Okay, that is all we have for this example.
Okay, many years ago, Ajahn have this kind of midterm examination problem, and let us working on this one. And for the cable over here is built basis on high strength steel. Okay, and it support the force of what? 25 kilonewton for F1, 50 kilonewton for F2, and then the cable have various dimension A, B, C, D, E. Okay, and if you look it, A is going to be 3.5 meter, B is 2 meter, C is 2.5 meter, D is 1.5 meter, and E is 2 meter, and then there is no F. There is no F. We are going to determine the F. This is going to be the what so called in English, which is called this one is a set. Okay, and then they ask us to determine various force in the cable. The first one is going to be F sub AB. F sub AB is going to be this one, and it's going to be F sub BC. F sub BC is going to be this one, and also F sub CD. Let me put this one, F sub CD. That's going to be the unknown. And then not enough from that, they're going to ask us to determine the total length of the cable. Okay, it's only required the knowledge from your trigonometry. Okay, and then they ask you to use the steel property. Let me change this one to 1080 megapascal because it is high strength steel. 360 megapascal is normal steel. It's not high strength steel. Okay, so by using the factor of safety of 3, I will say the sigma allowable for this cable is going to be 1080 megapascal divided by 3. So we will have sigma allowable of 360 megapascal. Ajahn, how come the factor of safety is 3, not 2? And if you observe, even though you go to Bung Thalua, you will see the cable subjected to sunlight, subjected to the rain, and sometimes it's also near the water. That's why we use large factor of safety. And also, it is the public area. The people use the bridge in the Bung Thalua as a public area. Okay, so putting factor of safety is 3 is important. Okay, for public safety. Now, what happened is, you may see this cable is supported by the pin at A and the pin at B. And again, you may say, okay, Ajahn, I will have the reaction to be D sub X, and this one to be D sub Y, this one to be A sub X, and this one to be A sub Y, you have 4 unknown. That is 4. Okay, that's 4 unknown. 4 unknown. Larger than 3 equation of equilibrium. Okay, and then what? Then we will use, okay, the cable concept. I just mentioned about the cable concept of reaction, okay, to analyze this cable. By doing this one, it require you guys to draw the free body diagram. Now, you got to project the cable from top to over here. Let me start from the top point. Okay, and let's say I'm going to project it for 5 centimeter. If Ajahn say this is 5 centimeter, it's going to be A. And I'm project it down for this one to another 5 centimeter. That is going to be D dot. And this is going to be point C. Point C. And this is going to be point B. 5 centimeter. So, based on copying the structure, you guys will have this cable A, B, B, C, and also the C, D. And Ajahn would like you guys to set up the reference axis. Let me put the reference axis close to here in the form of X and Y. Okay, and then based upon the previous concept that I have, this is going to be the joint, and the joint subjected to the next step, the no force, and this is 25 kilonewton. This is going to be 50 kilonewton. Under the application of the force, you have what? For sure, you're going to get the same reaction. Okay, but this one is inconvenient. Let me put this one to be R sub D. Okay, after this one R sub D, and this one to be R sub A. And by the concept, okay, of the reaction, this R sub D is going to be equal to the force T sub CD. Okay, Ajahn, can I use F? You may use F. F for the force, T for the tension. Okay, Ajahn may use T for this one. Okay, and then for this one, this R sub A is going to be what? Is going to be the force in cable AB, T sub AB. Now, you put the known force, you put the unknown force into the problem already. Then you need to put the dimension. What you have here is 2 meter, 2.5 meter, 1.5 meter. Okay, and then for this one, let me try to put the light. That's going to help. Not help much. Anyway, let's put the light. Okay, and then what you have this one is going to be 3.5 meter, and the distance between this one and this one is going to be 2 meter, and then we don't know the distance from here to here is going to be F. Now what you can do is you take the moment at A. You cannot take the moment at A because of what? You may project this one. Okay, but since you don't know F, you don't know the theta over here. Okay, this is going to be theta sub CD, and this is going to be theta sub CD. That is the problem. But if you notice over here, this is going to be theta sub AB. and this is going to be theta sub AB also. Okay, this is, and then you have this one for 3.5. You have this one for 2. Okay, you may have what? Tan of theta sub AB equal to 3.5 meter divided by 2 meter. Then basis upon this, theta sub AB will be arctan of 3.5 divided by 2. What you guys get is going to be 60.2. I get 255 degree. Now this is going to be 60.255 degree. Then Ajahn may project this one down here. This is going to be T sub AB, or you may set it to be R sub AB whatsoever. And that is going to be cosine of 60.255 degree. And also, if you project it over here, you will get this one to be T sub AB and sine 60.255 degree. Okay, now what you get is consider the free body diagram of the cable A, B, C, D, and then you do the summation of the moment about D equal to 0. Then T sub AB side going to rotate clockwise. So I put this one counterclockwise is no, sorry, this is clockwise positive. So you guys will get T sub AB and then sine 60.255 degree, and it's rotate about point D in this clockwise direction, and the distance measure from A to D is moment arm, and then you get this one to be what? 4, 6. You times this one by 6. Okay. Now you do again the moment about point D. T cosine theta going to rotate about D in opposite direction. Okay, this one will rotate in this counterclockwise direction minus T sub AB cosine 60.255 degree. The line of action of this one is going to be on this line, and the eccentricity is 2. So put this one into 2 meter. Okay, now 2.5 rotate counterclockwise, 50 rotates counterclockwise, minus 25 have the distance from here to here of 4, minus 25 times 4, and then 50, okay, is 1.5 minus 50, and then times 1.5, then you got it to be 0. If you carefully calculate it, you're going to get T sub AB, and then 6 sine 60.255 degree plus 2, okay, cosine of 60.255 degree, and then it's going to be equal to this 2 number is 175, and then you will get T sub AB equal to 175, and then divided by 4.2147, and then you will get this one to be 41.521 kilo Newton. Ajahn, you get this one? Yes, I get this one. 41.521 2 kilonewton. It is in tension. Okay. And then after you get this one, you will go a bit further to determine T sub CD. Okay. So basis upon this one, you may go to another point here. Then what you get is this one can be T sub CD and cosine theta sub CD. And this one can be T sub CD and sine theta sub CD. Oops, that is not good. Okay, sorry for moving it too far away. Okay, what did you get? You may use two more equation. So we determine, okay, T sub CD by what? It's up to you. Summation of x sub x, summation of x sub x equal to 0. What you get is this one T sub CD cosine theta sub CD. T sub CD cosine theta sub CD actually is can be this one d sub x. Okay, if you can say this, it can be d sub x, and this is going to be equal to this one T sub AB, and then cosine 60.255 degree. Okay, then you get the result of this one, since this one is 41.521. You get this is to be 20.62 kilonewton. Okay, this is going to be 20.62 kilonewton. Let me put it very clear, 20.62 kilonewton. And then if you do the upward, let me put it to be in vertical direction, you find T sub CD, or you may see this is D sub Y equal to T sub CD sine theta sub CD. That is what? That is upward. Then you can combine it. Okay, just combine it. Plus this one. Let me take this one out to make you less confused. Just take it out. Okay, we will know it later. Just be in our mind. Then this is plus 41.521 and sine 60.255 degree. Upward, and then is equal to this two, 25 plus 50. Then you get what? You get T sub CD and then sine theta sub CD. This is 75 and minus this one, we will get this one to be 38.96 kilonewton. Now, this is going to be 38.96 kilonewton. And then you get two equations. Let's say this is equation number 1. This is equation number 2. You put number 1 divide by number 2. You will get the equation of what? Number 2. T sub CD sine theta sub CD, and then you divide it by this one T sub CD cosine theta sub CD, and then it's equal to 38.96 divided by 20.62, and then what you get is this one cut to each other. Okay, you will get the equation to be tan of theta sub CD, okay, equal to 38.96 divided by 20.62. So zeta sub CD is going to be 10 arctan, okay, of 38.96 divided by 20.62. And then you're supposed to get this one to be 62.11 degree. So this is 62.11 degree. Okay. And then you just plug it back. Okay. For 1, we have what? T sub CD equal to this one, 20.62 and divided by cosine of what? Zeta sub CD 62.11. Please put it in your calculator. Okay. Yesterday I didn't get a correct one. Supposed to be 44.08 kilo Newton. Okay. And then this is 44.08. Just put it up. This is T sub CD 44.08 in tension. Okay. So we have two solutions already. The tension in this cable, the tension in this cable. Okay. But you don't know the tension in this green cable. We determine T sub BC, okay, by using the method of choice. What choice you are going to cut? That can be B, also can be C. It's up to you. Okay, so we may use the point B. Let me project the point B, okay, to over here. And let's say this is B. We have this one to be X. We have this one to be Y. We have the tension T sub AB 41.52. So put it in this direction. This is going to be 41.52 kilonewton. And then there is the force in BC. So this is going to be T sub BC. And then we have what? Next, we have the angle that's at over here. Zeta sub AB is 60.255. This is going to be 60.255 degree. And then what we have is what? The reaction that's X over here is going to be 25 kilonewton. And then what we don't have over here is going to be zeta sub BC. Now, the unknown is not only the force. The unknown is the force and the angle. Okay, don't worry. We are going to do the same as before. We just do the summation of x sub x equal to 0. What you get is this is going to be your T sub BC cosine zeta sub BC, right? And then put this one in positive. T sub BC cosine zeta sub BC. And then the projection over here is going to be equal to 41.52 and then cosine 60.255 degree. Okay, can you solve it? Not yet. Okay, and then we go a bit further. Let's say this is number 3. And then for the summation of f sub y equal to 0, this is upward. This is downward. Okay. We are looking for this one. I put the downward to be positive. So T sub BC and then project over here. Sine zeta sub BC and then plus 25. And then it's going to be equal to 60.52 and then upward. This is going to be sine 60.255. Then you rewrite this equation, you will get T sub BC, and that is going to be sine theta sub BC. Take this one to the right and minus this. This is going to be 11.039. And let's say this is number 4. Let me put this one into the calculator. You will get this one to be 20.6. Okay. 2. Okay. Just put it into your calculator. And then again, you solving for what? You're solving for the angle theta sub BC and T sub BC. Do the same thing. You may put equation number 4 divided by equation number 3. So 3 sub BC sine theta sub BC divided by T sub BC cosine theta sub BC, and then this is going to be what? 11.039 divided by 20.62. Okay, and then this one cut, and this is going to be tan of theta sub BC. Now, theta sub BC is going to be arctan. Okay, arctan of this one 0.5338, and then that is going to be 28.164 degree. Now you get the angle over here to be 28.16 degree. Or if you put it over here, okay, this is going to be 28.16 degree. And then you just plug this one back. So from, depend on which equation, 3, let's say this one, you will get T sub BC equal to this one, 20.62 divided by cosine of 28.16 degree. So this one is going to be 28.39 kilo Newton. So put it over here, 28.39 equation over here. Okay, then you get the result, this one. Okay, and then you get T sub AB, this one, and then you get T sub CD, this one. You can see from the result that you get which one is the largest. We should note, okay, note T sub CD is the largest tension, and I should say occurred at what? Occurred. You see this angle 62.11. Okay, for the yellow, the green 28.16, the orange 60.25. Okay, so occur at the largest theta. Okay, is the angle between the cable and the horizontal. This is very important. Okay, and then there is another thing. I think this one is 20.62. If you put this one into the calculation, let me put this one into the calculation. T sub AB, this is 41.52 cosine 60.25. If you put it in your calculator, you will get 20.62. Okay, again. For the force here, T sub BC. If you put it over here, it's going to be 23.39, and then cosine 28.16 degree. You get the result to be 20.62 kilonewton. Okay. Note number one. Note number two. Okay. T sub BC cos theta sub BC equal to this one. T sub AB cos theta sub AB equal to T sub CD cos theta sub CD equal to F sub H is equal to a constant horizontal force. Horizontal force in cable segment equal to a constant. Okay, we will talking about this later. This one going to be in the form of F sub H equal to T cosine theta, and then is equal to a constant. Okay, in short, we will use this to note on the cable subjected to uniformly distributed load. Now, let me move to the next word. Next, we're going to determine the length. Let's ask. Determine the length. Okay. L. Okay, L. L is going to be what? L is going to be L sub A B plus L sub B C plus L sub C D. Okay. By this one, you may say, Ajahn, it's really easy. Okay, this one is going to be square root 3.5 square and 2 square. 3.5 square plus 2 square. Okay. And then, do you know F yet? We don't know F yet. Can we determine F? Can we determine F? Can we determine F? Well, we can. We may put this one to be F divided by 1.5 is going to be tan of what? 62.11 degree, right? So you may have F equal to 2.835 meter. So this is 2.835 meter. So if you know this one, 2.835, this is 1.5, right? So you have plus square root of 2.835 square plus 1.5 square. You may get this is the length for CD. How about the length for this one? Okay. You know 2.5 here, right? And then you're going to find what the length BC. Now let me took it over here. We looking for the length. If you said cosine of 28.16 degree, it's going to be equal to what? It's going to be the length here. That is 2.5 divided by L sub BC, right? It's going to be horizontal length divided by the grid. So L sub BC is what? We may put it over here. L sub BC plus 2.5 divided by what? Cosine 28.16 degree. Now you will get the result. This one to be 10.074 meter. That is going to be our result, 10.074. This one, 10.40074 meter. Now, the final one, we determine our radius, right? This one. We have what? We have sigma equal to force divided by the area, right? We have what? We have area that we looking for, require. Take it up. It's going to be T max divided by sigma allowed. Now, what is our T max? Remember this one? This one? Remember this one? That is going to be our T max. It's going to be 44080 Newton. And then divided by our allowable. That is 360. And divided by 360 Newton per square millimeter. Then you get this one to be what? Put it into your calculator. That is going to be square millimeter, right? What did you get? No, not 0.1. It's going to be larger than that. 44080 divided by 360. 122.44. Okay. 122.44. So what is going to be radius? It's going to be this one, pi r square, right? So your r is going to be what you get. R is to be what? Square root pi r square. Pi r square equal to 122.44. Okay, this one is going to be 122.44 divided by pi and square root. Okay, that divided by 3.1416 and then take a square root 6.24. Okay, that is going to be equal to 6.24 millimeter. Okay, the diameter is going to be what? Diameter is going to be 12.28 millimeter. Recall from lab number 3. You test the deform bar, right? The size of what? 12 millimeter, right? That's a bit larger than that. Okay, for this cable, but this is high strength steel. Okay, have the yielding strength of 1080 megapascal. So that's all for this example.
This script is the demonstration on the example about the cable subjected to the concentrated load or point load. As you may know, the cable have been used in many engineering applications, such as the suspension bridge, the transmission line, and other structure. The cable generally may be divided into two types according to their loading. So what we are talking about the cable supporting the concentrated load. Okay, this is an example of the cable that support the concentrated load of the weight of the chairs and the skier. This picture shows how we transport the skier from the mountain to the other mountain. This cable system, composed of the column and the cable hanging from the column to another column, and then there is the cable that's sticked with the set of the seats that will let the skier, okay, sit over here, and then one of the cable gonna move to the right and another one gonna move to the left when they come. Okay, since the weight of the cable of the chairlift system is negligible compared to the weight of the chair and the skier, the method of this section can be used to determine the force at any point of the cable. So by consider the cable support the concentrated force, one of the assumptions that we put on is the weight of the cable is negligible. And due to the concentrated load or to the point load, the section of the cable will be in tension directed along the cable. So by considering this, actually we can consider the joist of the cable as the particle, and then we may use the concept of equilibrium of particle to determine the tension force along the cable. Okay, let us start by trying to solve this example to show you, and let us consider the cable system shown in this picture. The cable support the series of point load, okay, which are 80 kilonewton and 50 kilonewton. And to determine the force in each cable, okay, there is the assumption we should make here. The first the cable width is negligible, okay, compared to the point load. Okay, it's very small compared to 50 kilonewton and 80 kilonewton here. And the second, the cable is a two force member. Okay, and is subjected to tension. Most of the cable going to have the tension. Cable cannot take the compression, okay, due to the characteristic of the cable. And then what step we supposed to work to determine the force in each cable? The calculation procedure must be have the following step. First, usually we draw free body diagram of the cable system, okay, and use the equation of equilibrium to find reaction, okay, to find the reaction. Okay, and after you find the reaction, usually you cannot find the reaction directly. You may find the force in the cable near the reaction. I will mention this later. Okay, the second, since the cable can be assumed as the particle, so we draw free body diagram of each joist, and use the concept of equilibrium of particle, okay, to determine the force in each cable. So we use the equilibrium equation of equilibrium to find the force in each cable. That's the second one. So we will have all the forces in the cable. And then, like this example, you may determine the other parameter such as the sag edge and the total length. So you may also have the third, determine also required parameter such as over here H and L, okay. And the last one, they also ask us if the cable made with the structural steel of the yielding of 250 megapascal. The problem asks us to determine the radius of the cable cross section by using the factor of 2.5. So next step, you're going to determine the size of the cable, and in this one they have the allowable stress of 250. So you can determine the allowable stress of yielding stress divided by factor of safety. So we get the allowable stress of this structural steel of 100 megapascal. So the first one, we design the cable. Up until here, let's see, by using mechanics of material. We didn't study the steel design yet, so we will follow the mechanics of material procedure. Okay, that is the whole step that we have to consider this cable, and we also consider the assumption that we could use. Okay, let's start by the first step. Okay, we're going to draw the free body diagram of this cable. We start by projecting all the length for this, and then if you may mark this is the A. Okay, you also can measure the other to determine the other point. This is going to be 2 centimeter. Okay, you may just put this one for 2 centimeter, and this one going to be C. Okay, and you may have this one, if you like, project this. It's going to be 7 millimeter. So if you project this one and you measure another 7 millimeter, you will get this point of D. Okay, and the other from the D, you may measure for 2.4 millimeter. Okay, from D, but it's about 2.4 millimeter, and then you get the point B here. Okay, and then you can connect all the cable like this. If you like, you may give this one as the yellow, this one as the green, and this one as the orange. And then don't forget to make the reference axis of X and Y. Just this X and this Y, since we're going to use the equation of equilibrium to determine the forces in the cable. And after you copy the cable system and then put the no force, this is going to be 80 kilonewton. This is 50 kilonewton. Okay, under the action of the force, they're supposed to have the reaction. Okay, reaction. And since the A is the pin, okay, the A is going to have the two reaction, the A sub Y and A sub X, Y and A sub X. And also under the applied force, the B also have B sub X and B sub Y. So if we consider this point, we're going to have the total of 4 reactions, and you already have 3 equations of equilibrium. So we cannot solve, okay, for the reaction of this. One way we need to do is we're going to cut. You may cut this one. If you cut this one, you also can see that this portion of the cable gonna have the tension along it. Okay, and if you know this and you know the angle here, okay, you can determine the A sub X and A sub Y later. But what happened is at the A we have the unknown H, the sec length here, so we cannot determine the angle here. Okay, but for this size we have this one for 5 meter, and then we may find this reaction in the form of the tension along segment BD of this cable. So we get this one as unknown of the T sub BD, and we can set the ratio of this is 5, this is 3 meter. So we have this one for 5 and 3, and then the incline here is going to be 5 power 2 plus 3 power 2, that is going to be 34. Okay, this side can be used because we know the angle here, or we know the ratio here, so it can separate into this one. Okay, let's say this is going to be B sub X, and also project this one into the what's so called the B sub Y. Okay, but it was written in the form of resultant force of the component B sub X and B sub Y. By this way, the unknown now reduce from 1, 2, 3, 4 to 1, 2, and 3 only. Next, we put the other length into our problem. So we have this one for 3 meter and this one for 4 meter. Okay, now we draw the free body diagram of the cable system and we arrive at this. And next we're going to use the equation of equilibrium to determine the required reaction. Okay, this time if you may consider, it's going to be better if you take the moment about A, okay, to eliminate the unknown A sub x and A sub y. So summation of the moment about A equal to 0. And if you take the moment about A, the B T sub BD trying to rotate counterclockwise. So we have the counterclockwise rotate as positive. And what we have, if you project it in this one, it's going to be T sub BD. What T sub BD? It's going to have what? You project this force into the vertical. So it's going to have 5 divided by square root 34. That's 5 square root 34. And the line of action of this is going to be here. And it's going to be how far? 10 meter from point A. So the first one, we're going to have T sub BD. T sub BD. And going to rotate plus counterclockwise time 5 over square root 34. And then the moment arm is going to be the live action to A, that is 10 meter. 10. And then you have another one is the B sub x. And then you may know that your B sub x is going to be T sub BD. And it's going to be what? Horizontal time 3 divided by square root 34. And the line of action of this force is here. Okay. And by doing this, the rotation due to this B sub x is going to be clockwise. So this is going to be minus T sub BD and time 3 over square root 34. And what's the moment arm of this? If you may take a look from the pictures, okay, it said this is 2 meter. So put this one is 2 meter. So the moment arm is 2. And then if you may see, the 50 kilonewton gonna rotate clockwise. The 80 kilonewton gonna rotate clockwise. So just minus 50 kilonewton have the live action here. And the moment arm is gonna be 7. Okay, it's gonna be minus 50 and time 7. And 80 have the line of action here. That is 3 meter away from A. So it's gonna be minus clockwise minus 80 and gonna time 3. Okay, and then you get this equal to 0. Now you may stop the clips, okay, and put the number into your calculator to determine the T sub BD. Okay, break it. Okay, what do we have? Ajan get it for 78.19. That is the force in the yellow cable. Okay, and then you may determine the B sub x, B sub y. You also can determine the A sub x and A sub y. But since the problem didn't have any slot to put the A sub x, A sub y, or B sub x and B sub y in, they only require us to determine the force in each cable. So now we get the force in the table BD of 79.19. So this is going to be 78.19. Just put it here. And then we have 2 more of a cable to determine. Okay, and then we go to the step 2. Step 2, we're gonna draw the free body diagram. We're going to draw the free body diagram of joints. What joints do we have? Joint C and D. Okay, and then we will find the and find the T sub AC and T sub CD. Okay, and then C is here, D is here. Let us make the free body diagram. This is for the C, and this one is for the D, okay, it's going to be very close to like this. Let's see here. Okay, and then it's going to have the reference axis of X and Y of X and Y. And since we know the force in the yellow cable, okay, so we start by drawing the free body diagram of this one, and then we go to the C. So for the joint D, we have the force in this direction, and it's going to be 78.19. That is 78.19. And also we have this of what, of 3 square root 34, or if you may like, you may find the angle here. If you determine it, it's going to be 59.04. 59.04. Okay, and the point D subjected to the 50 kilonewton. So we got the 50 kilonewton in the vertical direction. And then on the orange line, we're going to have this one and this one. We don't know the force in the cable CD, so we put this one as the T sub CD. And since the T sub CD is tension, it's going to point out, okay, from the point C and the point D. So this is going to be T sub CD. And what happened is, we don't know the angle between T sub CD and horizontal line. So this is going to be the theta. And if this is theta, this also to be the theta. Okay, now we finish drawing the free body diagram of point D, the no force, the unknown force, and unknown angle. And at the point D, let's see, we have the force here of 80 kilonewton. And also it has the unknown force here, the green one, and what the direction is going to be like this. That is going to be T sub AC. And also you don't know the angle of this, so let it be free. And if you consider these two free body diagram, you may see the free body diagram of joint D has two unknown. Okay, however, the free body diagram of this joint C has 4 unknown. Okay, so thus we use the free body diagram of joint D first. Okay, we start by using this. If you use the free body diagram of joint D, let's move it a little bit here. You may start by summation of f sub x equal to 0. If you put this one in f sub x equal to 0, you may project this. Okay, this is going to be the unknown force. So put this one at the positive, and then you get T sub CD, and then it's going to cos theta. And also, if you project this one into this direction, it's going to point like this. So you're going to get this one for 78.19, and it's going to cos 59.04. Okay, and then you didn't get anything. This one gonna be T sub CD equal to, put this into your calculator, you will get this number of 78.19 cosine 59.04. You will get this one for 40.23, and then it's going to be cos theta, and you didn't get this, so this is going to be equation 1. And later you may move to summation of f sub x equal to 0. So f sub y equal to 0. And what we get here is if you put it into that, this one going to produce downward component. So put this downward at the positive. So you get this one for T sub CD, and put it in this direction. So it's going to be psi theta. Okay, and next, what is going to be? It's going to be what's downward, right? It's going to plus 50. Downward, it's going to plus 50. And then if you put this one, it's going to be upward. So it's going to be equal to 78.19 psi 59.04 degree. And then you move this one, you get the T sub CD equal to, you put this one into this one, that's going to be equal to 38.19 psi 59.04 minus 50. You should get it for 17.05. And then you may put, you may have this one for, this is going to be psi theta, and then equal to, you don't need to. Okay, this one going to be the equation 2. You just substituting 1 into 2. If you put this one into this, you will get this one for 40.23, and then divided by cosine theta, and then you have sine theta, and this one gonna be equal to 17.05. You can see that you obtain the tan theta now, right? You're going to get tan sine over cosine. That is going to be tan theta, and then this is going to be equal to 17.05 divided by 40.23. And if you put them into the calculator, the theta gonna be, you may pause the clips, okay, and try to check what you get for the theta here. You will get this one for 22.97 degree, okay, and then you may substitute this one back into equation 1. Okay, and then we may have T sub CD. T sub CD is here. T sub CD, and what is equal to 40.23, and then divided by cosine of 22.97 degree, and then you get T sub CD, which is the yellow cable of 43.69 kilonewton. Okay, this is going to be for the yellow cable. Now, the free body diagram of point C will change. Since you get the theta already, the theta going to be equal to 22.97 degree, and you also get T sub CD of 43.69 kilonewton. So the unknown reduced from 4 unknown, okay, to only 2 unknown is T sub AC and phi. Okay, next we move to find the force in cable AC. Okay, from the free body diagram of joint C, okay, again the unknown is the force and the angle. You just do the summation of x sub x equal to 0 again. This time when you project in the x, it's going to be in this direction, and again you put this one as the positive, and you will get T sub AC, and by this it's going to be cosine phi. And again, if you project T sub CD 43.69 into the x, it's going to be in opposite, so it's going to be equal to 43.69, and this one got a cosine of 22.97 degree. Okay, and following this, if you do some arrangement, you will get T sub AC equal to what? Put this number into your calculator. Stop the clip. Pause the clip. You will get this for 40.22, and it's going to divide it by cosine phi, and you will get this as the third equation. Now you do the summation again. Summation of x sub y equal to 0. That's the one, and then it's going to get this one upward. So that's upward is positive. This one is positive, and you get t sub ac psi, t sub ac psi phi. And then if you project this one, it's going to be up. This is 43.68 psi plus 69, and psi. This is psi what? 22.97 degree, and it's going to equal to 80. So this is going to be equal to 80. Again, you may write this one t sub ac psi phi, and then you just move this one to minus 80, and then you will get this one of 62.95, and it's going to be equation number 4. Now you do the same as before, trying to solve the equation to obtain the t sub ac and angle phi. So you substitute this part into this, so you will get this one for 40.22, and then divided by cosine phi. This is t sub ac, and then sine phi, and then you get this equal to 62.95. And if you rearrange this one, you will get sine phi over cosine phi. That is going to be tan phi, and tan phi is equal to 62.95, and then divided by 40.22. And again, you may do the calculation for the phi. You may pause the clip. What you get for the phi, it's going to be 57.42 degree. Okay, that is going to be 57.42, or if you put it over here, that is going to be the same as this. That is 57.42 degree. And let me put this one as the green line. And the last one, you just substitute this one back. Okay, and then you get t sub ac equal to 40.22 divided by cosine of 57.42 degree. And when you put this one into the calculator, what do you get? T sub ac. Okay, we got the t sub ac. You may pause and do the calculation. 74.69. Okay, we obtain all the required forces. Okay, and what we have is t sub ac is the green one, 74.69. This is 74.69 kilonewton. And t sub cd 43.69. This will be 43.69 kilonewton. And then let me make a note. Okay, we arrive at the angle here of 59.04, and we have the angle phi here 57.42. This is 57.42. This is a little bit smaller than this, and the green, we got the force here is 74.69, and the force in this cable for 78.19. So this is going to be the maximum tension force in the cable, and you may see that the maximum, the Tmax is occur in the cable. Okay, having the angle theta max. Okay, this is 59.04. This is going to be smaller right? And this equal smaller. So this one supposed to be one of the node that I put it here, the one. And the second, if you do the T sub BD, you do the T sub BD 78.19 and cosine 59.04 is going to be equal to the T sub AC. It's going to be equal to 74.69 and then cosine 57.42. This is going to be horizontal force, okay, and they are equal. If you put this one, this is going to be 40.22 kilonewton, or you may conclude that all F sub H is constant, or is have equal value for the green, for the yellow, or even for this orange. Okay, it's going to be 43.69 and the angle here is 22.97, and you may say it's going to be equal to 43.69 cos 22.97. That means all the horizontal component of the force in the cable, they are equal and constant. Okay, that is important note. Let me put this one here because we're going to use this observation in the cable subjected to the uniformly distributed. Next, the problem asks us to find the H and to find the total length. Okay, the third. Find the sec H. Okay, this is called the sec H, and you can see H over 3 is going to be the tan 50.42. So we have tan 57.42 degree is going to be equal to the H and divided by 3. Now you may have H is equal to 3 and then tan 57.42 degree. And if you put that into your calculator, you're going to get the H of 4.694. This is 4.694 meter for the set H. Okay. And now later you may find the length. Okay, find the total length L. Okay, and find the total L, that means we are going to find all the green, yellow, and orange. So the L is going to be, for the green, you have the H of 4.694. So it's going to be square root of 4.694 square plus this is 3 square. Okay. For the orange, we don't know this one yet. We know this is 4. Okay. And if you the cosine of 22.97, the cosine of 22.97 is going to be 4 divided by L. It's going to be 4 divided by LCD. Okay. And your LCD is going to be 4 divided by cosine 22.97, and then it's going to plus 4 divided by cosine 22.97 degree. And the last one is the length of this. This is 5 square root 34. So that is going to be square root 34. So the length you may compute is 15.75. This is going to be 15.75 meter. Okay, we got something here. The H is here, and this is going to be the L. And the last one, they ask us to design the cable. When you design the cable, you're going to take a look at the Tmax. Okay, you got to have the Tmax of 78.19. Okay, next we find R of the cable. Okay, and basis on what? Basis on Tmax of 78.19 kilonewton. And by doing this yellow cable will subjected to the force, okay, on both ends. And then by mechanics of material, if you cut this cable, okay, your cable will have the normal stress occur here, okay, and then the maximum normal stress is going to be what? Is going to come from the Tmax and then divided by the required area. And what we have is that sigma max by the mechanics of material is going to be equal to sigma allow, or equal to sigma max equal to allowable stress. The allowable stress here is going to be 100 megapascal, if you remember. Is also, if you note it, it's going to be 100 Newton per square millimeter. Okay, now we really like the equation. We put the A required to be the thing that we are looking for is going to be equal to Tmax. Tmax here is 78,190 Newton, and then it's gonna divide it by allowable stress. That is divided by 100 Newton per millimeter square, and then cut. You may get this one equal to 781.9 square millimeter. Okay, and now you can determine the radius by pi r square equal to 781.9 square millimeter. And then when you put this into your calculator, stop the clips and try to do it, you will get the radius of 15.8 millimeter. Okay, and now you determine the diameter. The diameter is going to be 31.6 millimeter. That is the answer of the radius. You put this into the slot there. Okay, and in the market, we didn't have the cable with not exactly 31.6 millimeter. We will have the diameter of 30 millimeter or 32 millimeter or even 34 millimeter. Which one you going to select? We can select the one that's larger than what we have here. So we select 32 millimeter. Okay, that is the end of the example that I demonstrate you how to work on this problem step by step. Okay, finally you just put what we have into the space here, and the length is going to be 15.75 and the h is going to be 4.694. Okay, that's all we have for the example.